We will build up to the statement of the principle of conservation of momentum by first defining the momentum of a system of objects, expressing Newton's second law for a system in terms of momentum, and then rearranging that to get the impulse momentum theorem for a system. By the way, this all concerns linear momentum as opposed to angular momentum, which concerns objects that are rotating and is a topic for another time. So we'll be talking about linear momentum, but I'll just say momentum and drop the word linear for brevity. All right, so the momentum of a system of objects. On the left here, I've got a system of three objects, three independently moving things, 1, 2, and 3 with their own velocity vectors indicated. And so our system, as defined by this collection, has a center of mass, a point whose coordinates we can find by these formulas. We find the weighted averages of the x coordinates of the objects and the y coordinates of the objects to locate this imaginary point in space, the center of mass. And as the objects move around, the center of mass, this imaginary point, will be moving as well. So it will have an instantaneous velocity, the VCM, which we can also find by taking the weighted averages of the x and y components of the velocities of the objects composing the system. And so here's that formula. To find the velocity of the center of mass of the system, we take the weighted averages of the velocity vectors of the individual objects. Okay, now on the right here, I've got the same exact system, the same three objects, but instead of showing their velocity vectors, I'm showing their momentum vectors. So we take each velocity vector and multiply it by the mass of the object to get a new vector that is in the same direction as the original one, but just scaled differently and with different dimensions. So we have momentum 3 in the same direction as velocity 3 here, and momentum 2 in the same direction as velocity 2, and momentum 1, same direction as velocity 1. And we could add these three momentum vectors to get what we would call the total momentum of the system. That's straight up the sum of the individual momentum, P1 plus P2 plus P3. So if I added those three up using the head to tail method, make a chain out of them, momentum 1, momentum 2, momentum 3, and draw in the vector that points from the very beginning of that chain to the very end of that chain, that would be the momentum of the system as a whole. So that would be the momentum of the system, that light blue vector that goes from the very beginning of the chain to the very end of the chain. So I've drawn that in here, the momentum of the system. So I want to relate the momentum of the system to the velocity of the center of mass. We notice in the numerator here of this definition, in this weighted average, the terms happen to be the momenta of the individual objects. M1, V1, that's the momentum of object 1 here, and so on. So our numerator is really the sum of the individual momenta, which is the momentum of the whole system. And our denominator, the sum of all the masses, I'll call it m_sis, the total mass of the system. So we're noticing that the velocity of the center of mass is exactly equal to the total momentum of the system divided by the mass of the system, the total mass. Rearranged, we define the momentum of the system as the sum of the momenta of the objects, which is also equal to the mass of the system, the total mass, times the velocity of the center of mass. In this vector equation, we see that these two vectors will be parallel to each other. So whatever direction your VCM is, the momentum of the system will be a vector in that same direction. And since it's a vector equation, we can represent it as individual equations for each component. So the x component of the momentum of the system equals the mass of the system times the x component of the VCM, and so on. What this statement is saying is that we can treat this collection of objects as if it were a single object of mass m_sis located at this imaginary point, the center of mass, and moving with velocity VCM, carrying with it a total momentum equal to msys times VCM. We can replace this collection of three objects with a single object there, moving in a direction parallel to the VCM, carrying all the momentum of the system with it. We see the VCM is parallel to the momentum of the system.